Welcome to Sleepy Parallax. It's lovely to have you here with us tonight. Let's start at the very beginning, though not quite at the Big Bang itself. That moment, roughly 13.8 billion years ago, was when everything began. Space, time, matter, and energy all burst into existence in a singularity we still struggle to fully comprehend. But the Milky Way story doesn't start quite that early. There needed to be time for things to cool down, for the universe to expand, and for the first structures to begin taking shape in what had been, for a brief while, an almost perfectly smooth sea of hydrogen and helium. For the first few 100 million years after the Big Bang, the universe was dark. It's strange to imagine a cosmos without starlight, but that's exactly what existed during what astronomers call the Dark Ages. The universe was expanding and cooling. The primordial soup of particles was settling into atoms. Hydrogen and helium, forged in the first 3 minutes after the Big Bang, drifted through the expanding void. There was also something else, something invisible and mysterious that made up most of the matter in the universe. We call it dark matter, and though we still don't fully understand what it is, we know it was absolutely essential for galaxy formation. Dark matter doesn't interact with light. It doesn't emit anything, doesn't reflect anything, doesn't absorb anything. It's completely invisible to every telescope we've ever built. But it does have mass, and where there's mass, there's gravity. As the universe expanded, tiny variations in density, quantum fluctuations from the Big Bang itself, were stretched across space. Dark matter began to clump together in the denser regions, drawn by its own gravity. These clumps grew slowly at first, pulling in more dark matter and the ordinary matter around them. Think of them like seeds planted in cosmic soil. They were small at first, barely noticeable against the vast backdrop of space, but they had gravity on their side, and gravity is patient. Over millions of years, these dark matter halos grew larger and more massive. The hydrogen and helium gas began to fall into these invisible gravitational wells, accumulating at their centers. Somewhere between 13 and 13.6 billion years ago, in a region of space that would eventually become part of what we call the local group. One of these dark matter halos was forming. It wasn't particularly special at first. Countless similar structures were taking shape across the universe. But this particular collection of dark matter and gas, would eventually become our home. It would become the Milky Way. The gas falling into this dark matter halo didn't arrive all at once. It came in streams and clumps, each with its own story, its own origin in the cosmic web. As the gas accumulated, it began to heat up. Gravity compresses matter and compression generates heat. Eventually, in the densest regions, the conditions became extreme enough for something miraculous to happen. Nuclear fusion ignited. The first stars were born. These weren't stars like our sun. The very first generation of stars, what astronomers call population 3 stars, were massive beyond anything we see today. They contained only hydrogen and helium because nothing heavier existed yet. Every other element, every atom of carbon, nitrogen, oxygen, iron, everything we're made of had to be forged inside stars first. These early giants burned incredibly hot and died incredibly young, exploding in supernovae that scattered the first heavy elements into the surrounding gas. But the Milky Way's oldest stars aren't quite that old. Population 3 stars are theoretical. We've never actually observed one because they all died billions of years before our galaxy fully formed. The oldest stars we can see in the Milky Way are population 2 stars, found primarily in globular clusters and the stellar halo. These ancient suns are roughly 12 to 13 billion years old, and they represent the second generation of star formation, enriched with just a tiny sprinkling of heavier elements from those first massive stars. Picture the proto-Milky Way as it existed 13 billion years ago. It was nothing like the majestic spiral we know today. Instead, it was a chaotic, turbulent cloud of gas punctuated by clusters of young stars. There was no organized disk, no spiral arms, no elegant structure. It was messy and violent, with gas clouds colliding, shock waves triggering bursts of star formation, and young stars lighting up the darkness with their fierce blue-white glow. These early star-forming regions weren't evenly distributed. They clumped together, creating dense clusters that we now call globular clusters. If you've ever looked at a globular cluster through a telescope, perhaps the famous Hercules cluster or Omega Centauri, you've seen some of the oldest structures in our galaxy. These spherical collections of hundreds of thousands of stars are like fossils, preserved snapshots of what star formation looked like in the galaxy's infancy. The dark matter halo continued to grow. It pulled in more gas, more dark matter, and more of these early star-forming clumps. Some of those clumps were actually small dwarf galaxies in their own right, complete with their own dark matter halos and populations of stars. As they fell into the growing proto-Milky Way, they were torn apart by tidal forces. Their stars were scattered, but they weren't destroyed. Many of them still orbit today in the stellar halo, following elongated paths that betray their violent origin. During this early phase, the gas that would eventually form the Milky Way's thick disk began to accumulate. Recent research has revealed something remarkable about this period. The thick disk, a pancake-shaped population of old stars that's thicker and puffier than the thin disk we're part of today, started forming incredibly early. We're talking about just 800 million years after the Big Bang. That's remarkably soon in cosmic terms, and it suggests the Milky Way got off to a fast start. But the structure of the galaxy during this time was still primarily spherical. The gas and dark matter formed a roughly spherical distribution, and the older stars orbited in all directions, not in an organized disk. It would take a major event, a cosmic catastrophe of sorts, to transform this messy proto-galaxy into something with more structure. That event was coming, and it would reshape the Milky Way forever. For the first couple of billion years, our galaxy grew through a process astronomers call hierarchical assembly. Small structures merged to form larger ones. Dwarf galaxies fell in and were absorbed. Gas streams flowed inward, feeding star formation. It was a gradual process, messy and chaotic, but effective. The Milky Way was building itself piece by piece from the fragments of smaller galaxies and primordial gas clouds. The globular clusters formed during this era are particularly special. They're among the few structures from the Milky Way's youth that have survived relatively intact to the present day. When you look at a globular cluster, you're seeing stars that have been together for most of the history of the universe. They've orbited through the galaxy countless times, witnessed the birth and death of billions of stars, and yet they've held together through their mutual gravity. Some of these globular clusters contain hundreds of thousands of stars packed into a sphere, only a few hundred light-years across. If you lived on a planet orbiting a star in the center of a globular cluster, your night sky would be spectacular beyond imagination. Thousands of stars would be bright enough to cast shadows. The collective light would be enough to read by. And unlike our Sun, which is relatively isolated with the nearest star more than 4 light-years away, stars in globular clusters can be separated by mere light weeks or even light days. As the first couple of billion years passed, the proto-Milky Way was becoming more massive, more organized, and more recognizable as a galaxy. But it was still missing something. It didn't have the prominent disk and spiral arms we see today. It didn't have a clear distinction between different stellar populations, and it hadn't yet experienced the transformative event that would give it the structure we're familiar with. That event, a massive collision with another galaxy, was approaching through the darkness of intergalactic space. Approximately 11 billion years ago, something extraordinary happened. Another galaxy, now known as Gaia-Enceladus, or sometimes called the Sausage Galaxy, because of the shape of its stellar debris, slammed into the young Milky Way. This wasn't a gentle merger. This was a cosmic train wreck, a collision between two massive structures that would fundamentally reshape our galaxy. The discovery of this ancient collision is a relatively recent development in astronomy. For decades, astronomers suspected that the Milky Way had grown through mergers, but the details were murky. Then came Gaia, a European Space Agency mission launched in 2013 with the specific goal of measuring the positions and motions of more than 1 billion stars in our galaxy. When the second data release came out in April 2018, it revolutionized our understanding of the Milky Way's history. A researcher named Amina Helmi and her team began analyzing the Gaia data, looking at not just where stars were, but how they were moving. Most stars in the disk of our galaxy orbit in roughly circular paths around the galactic center, all going in the same direction like cars on a circular highway. But Helmy found something strange. There was a population of stars moving in completely different ways, with elongated orbits that carried them plunging through the disk and then back out into the halo. Within days of the data release, another researcher, Leiden University PhD student Helmer Koppelman, made a similar discovery. He processed the data and immediately recognized what he was seeing. In every direction he looked, he found stars with peculiar orbits, all ping-ponging through the inner galaxy in the same unusual pattern. The statistical signature was unmistakable. These weren't random stars following random paths. They were the remnants of a dwarf galaxy that had been torn apart by the Milky Way's gravity billions of years ago. The realization was stunning. Perhaps half of all the stars in the inner 60,000 light-years of the halo, an enormous number of stars came from this single ancient collision. The intruder galaxy had been substantial, maybe as much as 10% of the Milky Way's mass at the time. This wasn't a minor merger. This was a major event that would have been visible from across the universe if anyone had been watching 11 billion years ago. Let's imagine what happened during this collision. The Gaia-Enceladus galaxy, a dwarf galaxy perhaps 1/10 the mass of the proto-Milky Way, was drawn in by gravity. It had its own dark matter halo, its own population of stars, its own clouds of gas. As it approached, tidal forces began to pull at it, distorting its shape. But it was still intact, still recognizable as a separate galaxy when it made its first pass through the Milky Way's disk. The collision between galaxies isn't like the collision between two solid objects. Galaxies are mostly empty space. The distances between stars are so vast that actual stellar collisions would have been extraordinarily rare, perhaps non-existent. But the gas clouds? That's a different story entirely. When the gas from Gaia-Enceladus crashed into the gas in the proto-Milky Way's disk, it compressed. Shock waves propagated through the gas, and wherever gas is compressed rapidly, stars begin to form. The star formation rate in the Milky Way exploded. 11 billion years ago, our galaxy experienced a period of starbirth more intense than any time before or since. New stars blazed into existence by the millions. Massive stars, medium-sized stars, small red dwarfs, they all formed in this era. The light from all these young, hot stars would have made the galaxy shine brilliantly. If there had been astronomers in other galaxies looking our way, they would have seen a starburst galaxy, a galaxy going through a phase of unusually intense star formation. The collision didn't just trigger star formation, it also disrupted the existing structure. Stars that had been peacefully orbiting in the proto-Milky Way's thick disk were kicked up into higher orbits. These splash stars, as astronomers call them, were flung into the halo. Today we can identify them because they have different chemical compositions from true halo stars. They contain more iron relative to other elements, a telltale signature that they originated in the disk rather than the halo. The Gaia-Enceladus galaxy didn't survive the encounter intact. After its first plunge through the Milky Way, it swung back around, drawn by gravity, and crashed through again. And again. Each passage stripped away more of its stars, scattered more of its gas, and dragged it deeper into the gravitational well. Over hundreds of millions of years, the intruder galaxy was completely torn apart. Its stars were scattered throughout the Milky Way's halo. Its gas was mixed with the Milky Way's gas. Its dark matter halo merged with the Milky Way's dark matter halo. Today, billions of years later, we can still see the evidence of this ancient catastrophe. The orbits of those halo stars moving on their elongated paths tell the story. The chemical compositions of the stars, subtly different from their neighbours, tell the story. Even the ages of the stars, with a spike of stars all formed around the same time 11 billion years ago, tell the story. The Gaia-Enceladus galaxy is gone, but its legacy is written into the structure of the Milky Way. This collision had profound effects on the subsequent evolution of our galaxy. The burst of star formation consumed much of the available gas. The kinetic energy from the collision heated up the remaining gas, making it harder for new stars to form for a while. The thick disk, which had been forming steadily, was disrupted and enriched with stars from the collision, and the stellar halo was substantially populated with stars from the destroyed dwarf galaxy, After the merger was complete, after the last of Gaia-Enceladus had been absorbed, the Milky Way entered a new phase. The thick disk, now fully established, contained a mixture of original Milky Way stars and stars scattered during the collision. This disk was about 3,000 light-years thick, far puffier than the thin disk that would form later. The stars in the thick disk orbit the galactic center with a wide range of inclinations, some tilted significantly from the plane of the galaxy. But then, roughly 8 billion years ago, something changed. The thick disk ran out of gas. Without fresh material to feed star formation, the rate of new star birth in the thick disk dwindled and eventually stopped. The stars that had already formed continued their orbits, gradually aging from hot blue giants to cooler red giants, but no new stars joined their ranks. At the same time, fresh gas from the outer reaches of the galaxy began to settle into a new structure. This gas hadn't been part of the collision. It was pristine material that had been orbiting in the outer halo, slowly falling inward. As it fell, it conserved its angular momentum, causing it to settle into a thinner, more organized disk. This was the birth of the thin disk, the part of the galaxy we inhabit today. The thin disk is younger, more organized, and contains more heavy elements than the thick disk. Stars in the thin disk, including our Sun, orbit in a much flatter plane, all going in the same direction like a cosmic carousel. The gas and dust in the thin disk continue to form new stars today, though at a much slower rate than during the peak of the merger 11 billion years ago. The Gaia-Enceladus collision was the defining moment in the Milky Way's youth. It transformed our galaxy from a chaotic collection of gas and stars into something more structured and recognizable. It triggered the most intense period of star formation in our galaxy's history, and it populated the halo with billions of stars that we can still study today to understand what happened all those billions of years ago. But here's something remarkable about the Milky Way. Since that great collision 11 billion years ago, our galaxy has been remarkably quiet. There haven't been any other major mergers. No other large galaxy has crashed into us and disrupted everything. The Milky Way has continued to absorb small dwarf galaxies. It's still doing that today, but nothing on the scale of Gaia-Enceladus. This relative peace has allowed the thin disk to form and persist, and it's given spiral structure time to develop. Many other galaxies haven't been so lucky. They've experienced multiple major mergers, each one disrupting their structure and triggering bursts of star formation. Some have merged so many times that they've used up all their gas and stopped forming stars entirely, becoming what astronomers call red and dead elliptical galaxies. But the Milky Way has had 11 billion years of relative calm to develop into the spiral galaxy we know today. Now that we've followed the Milky Way through its violent youth and into its more peaceful adolescence and adulthood, let's take a tour of its structure as it exists today. If you could somehow step outside our galaxy and view it from above, what would you see? What are the major components and how do they all fit together? Let's start at the very center. The heart of the Milky Way is the galactic bulge, a roughly spherical or slightly elliptical collection of old stars that dominates the central region. This bulge contains billions of stars packed much more densely than in the disk. If our Sun were located in the bulge instead of out here in the disk, our night sky would be dramatically different. We'd see thousands of stars bright enough to be prominent, and the combined light would make true darkness impossible. The bulge isn't perfectly spherical. Recent observations have revealed that it's actually shaped more like a peanut or a bar when viewed from certain angles. This brings us to one of the Milky Way's most important structural features, the galactic bar. The Milky Way isn't just a spiral galaxy, it's a barred spiral galaxy, meaning it has an elongated structure of stars extending from the central bulge. This bar is roughly 27,000 light-years long from end to end, though measurements vary depending on exactly how you define its boundaries. It's made up of stars orbiting in elongated paths that are aligned with the bar's axis. These orbits are stable because of the way the gravitational forces balance out. The bar rotates as a solid structure, not quite like a solid bar of steel, but more like a coherent pattern of orbits all moving together. The discovery that the Milky Way has a prominent bar was actually surprising when it was confirmed. For a long time, astronomers weren't sure if we had a bar or not because we were inside the galaxy looking out. and it's hard to see the forest when you're standing among the trees. But infrared observations, which can penetrate through the dust that blocks visible light, revealed the bar clearly. It's one of the defining features of our galaxy's structure. From the ends of this bar emerged the spiral arms. For decades, astronomers debated how many major spiral arms the Milky Way has and exactly where they are. The challenge is that we can only see part of the galaxy from our vantage point. An interstellar dust blocks our view in many directions. But through painstaking observations using radio telescopes, infrared telescopes, and by measuring distances to thousands of young stars and gas clouds, astronomers have gradually mapped out the spiral structure. The current understanding is that the Milky Way has two major spiral arms and several minor arms or spurs. The two major arms are the Perseus arm and the Scutum Centaurus arm. These are the most prominent features, containing the highest densities of both young, bright stars and older red giants. They emerge from the ends of the central bar and wrap around the galaxy. The Perseus arm is particularly impressive. It's more than 60,000 light-years long and about 1,000 light-years wide. When we look toward the constellation Perseus in our night sky, we're looking along this arm, seeing some of its star-forming regions and star clusters. The arm has a gentle spiral pattern with a pitch angle of about 9 degrees, meaning it's not tightly wound but has a gradual, graceful curve. The Scutum Centaurus arm is equally grand, emerging from the opposite end of the bar and sweeping around the other side of the galaxy. Together, these two major arms give the Milky Way its spiral appearance when viewed from outside. But they're not permanent structures carved in stone. Spiral arms are actually density waves, patterns that move through the disk like waves on water. Stars and gas clouds drift in and out of the arms as they orbit the galaxy. When they enter an arm, the increased density triggers star formation, which is why spiral arms appear bright and blue. They're lit up by massive young stars that form there. Then there are the minor arms. The Sagittarius arm lies closer to the galactic center than our position. When we look toward the constellation Sagittarius, toward the center of the galaxy, we're looking through this arm. It's rich in gas and dust, with many star-forming regions visible as glowing nebulae. The outer arm, as its name suggests, lies farther from the center than the major arms. And then there's the arm we care most about, the one we call home. The Orion arm, also known as the Orion spur or local arm, is a smaller feature located between the Sagittarius and Perseus arms. For a long time, astronomers weren't sure if it deserved to be called a spiral arm at all. Some thought it was just a spur or bridge connecting two major arms, but recent observations have shown that it's more substantial than previously thought. The Orion arm is about 3,000 light-years wide and stretches for about 20,000 light-years. It has its own coherent structure and star-forming regions. It contains some of the most famous objects in our night sky, including the Orion Nebula, the Cygnus Rift, and countless star clusters. Most importantly for us, it contains our solar system. We're located on the inner edge of the Orion arm, about 26,000 light-years from the galactic center. That's roughly halfway between the center and the edge of the disk in what you might call the galactic suburbs. It's a relatively quiet neighborhood by galactic standards. We're not in the crowded bulge where stars are packed close together, and we're not on the sparse outer edge where stars are few and far between. We're in a comfortable middle ground, which may have been important for the development of life on Earth. The disk itself comes in two varieties, as we mentioned earlier. The thin disk is where most of the action happens today. It's only about 1,000 light-years thick, but stretches about 100,000 light-years across. That's a ratio of about 1 to 100, making it extraordinarily flat. If you scaled the Milky Way down so the disk was the size of a pancake, it would be thinner than the pancake. The thin disk contains most of the galaxy's gas and dust, and that's where new stars are forming today. It's also where you'll find the spiral arms, because spiral arms are regions where gas has been compressed enough to trigger star formation. The thin disk is relatively young, with most of its stars less than 8 billion years old. Our Sun, at 4.6 billion years old, is actually a middle-aged member of the thin disk population. Above and below the thin disk sits the thick disk, that older population we discussed earlier. It's about 3,000 light-years thick and contains stars that are mostly between 8 and 13 billion years old. These stars have more eccentric orbits and move with more random velocities than thin disk stars. They're the legacy of the galaxy's more turbulent youth, including stars scattered by the Gaia-Enceladus collision. Beyond the disks lies the stellar halo, a roughly spherical distribution of stars and globular clusters that extends hundreds of thousands of light-years from the galactic center. The halo is sparsely populated compared to the disk. If you lived on a planet orbiting a halo star, you might see only a handful of stars visible to the naked eye, and the Milky Way would appear as a distant glowing disk rather than a band across the sky. The halo stars are predominantly old, many of them dating back to the first billion years of the galaxy's existence. They orbit in all directions, not following the organized pattern of the disk. Some have highly elongated orbits that take them from the outer reaches of the halo deep into the galaxy and back out again. These are the stars that tell us about the Milky Way's merger history. But there's something else in the halo, something we can't see but know must be there. The dark matter halo extends even farther than the visible stars, perhaps out to 600,000 light-years or more. This invisible halo contains most of the galaxy's mass. The stars, gas and dust that we can observe make up only about 15% of the total mass. The rest is dark matter, and we know it's there because of its gravitational effects. The way stars and gas orbit the galaxy only makes sense if there's much more mass present than we can see. Stars in the outer parts of the disk orbit at speeds that would fling them into intergalactic space if the galaxy's mass was only what we observe in stars and gas. The extra gravity from dark matter is what keeps everything bound together. It's the scaffolding that holds the galaxy's structure in place. If you could see dark matter, the Milky Way would look completely different. The luminous disk and bulge would appear as a relatively small structure embedded in a vast, roughly spherical halo of dark matter. That halo is what defines the galaxy's true boundaries and provides the gravitational potential well that everything else sits in. Let's talk about dimensions. The Milky Way is enormous, but it helps to put some numbers to it. The disk is approximately 100,000 light-years in diameter, though there's no sharp edge. It just gradually fades out as you go farther from the center. The thin disk is about 1,000 light-years thick at our location, though it gets thinner closer to the center and thicker farther out. The galaxy contains somewhere between 200 billion and 400 billion stars. That's a staggering number, and the uncertainty in the estimate tells you something about how difficult it is to count stars in our own galaxy. We can't see all of them. Many are hidden behind dust. Many are too faint to detect. Some are in regions we simply can't observe well because they're blocked by the bright bulge or located in the crowded central regions where individual stars blend together. The total mass of the galaxy is about 1 to 1.5 trillion times the mass of the Sun, but remember, most of that is dark matter. The mass in stars is probably around 60 billion solar masses, and the gas and dust adds another few billion. It's a massive structure by any standard, though by no means the largest galaxy in the universe. There are elliptical galaxies that dwarf the Milky Way, and even our neighbour Andromeda is somewhat larger and more massive. The whole structure rotates, but not like a rigid disk. Objects closer to the centre orbit faster, and objects farther out orbit more slowly, a phenomenon called differential rotation. At our position, the solar system orbits the galactic centre at about 220 kilometers per second. At that speed, it takes us approximately 230 million years to complete one orbit. That means in the entire time dinosaurs have existed, then went extinct and humans evolved, our solar system has completed less than 2 full orbits around the galaxy. This rotation is what keeps the disk stable. The stars and gas aren't just sitting there held up by some mysterious force. They're all in orbit, constantly falling toward the center but also moving sideways fast enough that they miss and keep going around. It's the same principle that keeps planets orbiting the Sun or satellites orbiting Earth, just on a much grander scale. The spiral arms themselves don't rotate at the same speed as the stars. They're density waves, patterns that rotate more slowly than the material moving through them. Imagine a traffic jam on a circular highway. The jam itself might move slowly or even stay in one place while cars flow through it. The cars enter the jam, slow down, get bunched together, then accelerate back to normal speed as they exit. That's essentially what happens in a spiral arm. Gas and stars flow into the arm, get compressed, and then flow out the other side. This compression is what triggers star formation in spiral arms. When gas clouds collide and get squeezed together, their density increases. If the density gets high enough, gravity takes over and the cloud fragments into clumps that collapse to form new stars. The massive stars that form shine brightly and only live for a few million years, so they don't have time to move far from where they were born. That's why spiral arms appear bright and blue. They're lit up by these young massive stars even though the stars themselves don't stay in the arm forever. The Milky Way's structure is elegant and intricate. From the dense central bulge to the elongated bar, from the graceful spiral arms to the sparsely populated halo, each component has its own story and its own population of stars. And at the heart of it all, binding everything together with its immense gravity, is an object so dense and dark that not even light can escape from it. At the exact center of the Milky Way, 26,000 light-years from Earth, in the direction of the constellation Sagittarius, there lurks something extraordinary. It's not a star, though it's surrounded by stars. It's not a cloud of gas, though gas swirls around it in a blazing accretion disk. It's a supermassive black hole, and we've named it Sagittarius A, pronounced Sagittarius A star. Sagittarius A is a monster, though by supermassive black hole standards it's actually fairly modest. It contains about 4.3 million times the mass of our Sun, all compressed into a region smaller than the orbit of Mercury. That's an almost incomprehensible density. The gravitational pull at the event horizon, the point of no return beyond which even light cannot escape, is so intense that space and time themselves are warped beyond recognition. The discovery of Sagittarius A is a story that spans decades and involved multiple lines of evidence gradually converging. It started in the 1970s when astronomers detected a compact radio source at the galactic center. They called it Sagittarius A because it was the brightest radio source in the Sagittarius region. The asterisk was added later to distinguish the compact central source from the large radio emission around it. But detecting a radio source doesn't prove you found a black hole. Radio emission comes from many things: hot gas, pulsars, supernova remnants. What astronomers needed was evidence that something incredibly massive occupied a very small volume at that exact location, and the best way to prove that was to watch stars orbiting around it. In the 1990s, two teams of astronomers began a long-term monitoring campaign. Reinhard Genzel led a team using telescopes in Chile, while Andrea Ghez led a team using the Keck telescopes in Hawaii. Their goal was ambitious: to track individual stars in the chaotic, crowded environment of the galactic center with enough precision to measure their orbits. It required cutting-edge technology called adaptive optics, which compensates for the blurring effect of Earth's atmosphere, and extraordinary patience. Year after year they took images. They catalogued stars. They measured positions. And slowly, orbits began to emerge from the data. One star in particular, designated S2, became famous. This star has an incredibly tight orbit around Sagittarius A, swinging as close as 17 light-hours from the black hole, about 4 times the distance from the Sun to Neptune. But at that scale and that location, it's practically skimming the surface. S2 completes one orbit in just 16 years. Astronomers have now observed it go around more than once. They've measured how it speeds up as it approaches closest approach, reaching a staggering 2% of the speed of light. They've seen how its orbit shifts slightly each time around due to relativistic effects predicted by Einstein's general relativity. And most importantly, they've used its orbit to calculate the mass of whatever it's orbiting. The math is inescapable. To make S2 move the way it does, to whip it around in that tight ellipse at those incredible speeds, requires something with about 4 million solar masses concentrated in a region smaller than our solar system. There's no known object that can pack that much mass into such a small volume except a black hole. The evidence is overwhelming, confirmed by dozens of other stars with similar orbits. For their groundbreaking work, Genzel and Ghez were awarded the Nobel Prize in Physics in 2020, sharing it with Roger Penrose for his theoretical work on black holes. It was a fitting recognition of decades of meticulous observation and analysis. They had proven beyond reasonable doubt that our galaxy harbours a supermassive black hole at its heart. But the story doesn't end with detection. In 2022, something even more remarkable happened. The Event Horizon Telescope, a global network of radio dishes working together as a planet-sized telescope, released the first image of Sagittarius A, or rather they released an image of its shadow, the dark silhouette of the event horizon surrounded by a glowing ring of superheated gas and plasma. The image looks like a blurry orange donut. Not exactly the crisp photograph you might imagine, but it's one of the most significant images in the history of astronomy. It shows the direct visual evidence of the event horizon, the boundary beyond which nothing can escape. The ring is created by light from gas swirling around the black hole at nearly the speed of light. Some of that light is bent by the black hole's intense gravity, creating a bright ring that appears larger than the actual event horizon. What makes this image so challenging is that Sagittarius A is surprisingly small from our vantage point. Despite being supermassive, it's 26,000 light-years away, making it appear about the same size in the sky as a donut on the moon as viewed from Earth. Capturing an image at that resolution required unprecedented coordination and data processing. The EHT team had to synchronize observations from telescopes around the world, collect petabytes of data, and spend years processing it to produce the final image. The black hole itself doesn't emit light. That's why it's black. But the material around it, the accretion disk, blazes with energy. As gas spirals inward, friction and magnetic fields heat it to millions of degrees. This superheated plasma emits radiation across the electromagnetic spectrum, from radio waves to X-rays. The radio emission is what the Event Horizon Telescope detected, but other telescopes observing at different wavelengths see the same active region. Interestingly, Sagittarius A is currently relatively quiet for a supermassive black hole. It's not actively feeding on a large amount of material. Most supermassive black holes at the centers of galaxies are either in an active phase, where they're consuming gas and shining brilliantly as quasars or active galactic nuclei, or in a quiescent phase like Sagittarius A. Our black hole occasionally flares up when a clump of gas or an unlucky star gets too close, but most of the time it's calm. This might be fortunate for life in our galaxy. When supermassive black holes are actively feeding, they can emit tremendous amounts of radiation and drive powerful jets of particles and energy that stream out along the rotation axis. These jets can extend for thousands or even millions of light years, sterilizing huge regions of space with their intense radiation. A strongly active Sagittarius A might have made life in the Milky Way much more difficult, or even impossible. The immediate surroundings of Sagittarius A are hostile in the extreme. Stars orbit in a dense stellar cluster where close encounters between stars would be common. The radiation environment is harsh, and occasionally something dramatic happens. In 2020, astronomers observed a gas cloud designated G2 make a close approach to the black hole. Many predicted it would be torn apart and consumed, creating a bright flare. Instead, it survived, suggesting it might have been a star shrouded in a dusty envelope rather than a simple gas cloud. But stars aren't always so lucky. When a star wanders too close to a supermassive black hole, tidal forces can rip it apart in an event called tidal disruption. The star is stretched like taffy, with the side closer to the black hole pulled more strongly than the far side. Eventually it's shredded. Some of the stellar material falls into the black hole, creating a bright flare that can be detected from across the universe. Some is flung away at high speed. It's a violent end for a star, but it provides astronomers with a way to study black holes in distant galaxies. The physics near a black hole becomes increasingly strange as you approach the event horizon. Time itself runs slower in strong gravitational fields, an effect called gravitational time dilation. If you could somehow survive near the event horizon of Sagittarius A and watch the universe around you, you'd see time outside passing at an accelerated rate. Stars would appear to move faster in their orbits. The universe would seem to age more quickly. At the event horizon itself, time effectively stops from the perspective of an outside observer. If you watch something fall into a black hole, you'd see it slow down as it approached the event horizon, becoming dimmer and redder as the light stretched to longer wavelengths. It would appear to freeze at the horizon, though in reality it had already crossed and fallen in. From the perspective of the falling object, however, it would sail through the horizon and continue falling toward the singularity at the centre. The singularity is where our understanding of physics breaks down completely. General relativity predicts that all the mass of the black hole is compressed to an infinitely small point of infinite density. But infinity is usually nature's way of telling us our theory is incomplete. Most physicists believe that quantum effects, which general relativity doesn't account for, become important at such extreme scales and prevent a true singularity from forming. But without a theory of quantum gravity, we can't say for certain what happens there. Sagittarius A is surrounded by a dense stellar cluster. Millions of stars orbit within a few light years of the black hole, packed far more densely than stars in our neighbourhood. If you lived on a planet in that region, your night sky would be spectacular but also dangerous. The radiation from all those stars and from the black hole's accretion disk would be intense. Nearby supernovae would be relatively common, and the gravitational perturbations from passing stars might occasionally destabilize planetary orbits. Some of the stars near Sagittarius A are particularly unusual. There's a population of young, massive stars that shouldn't be there at all. These stars are only a few million years old, far too young to have migrated to the galactic centre from star-forming regions elsewhere. But forming stars that close to a supermassive black hole should be nearly impossible. The tidal forces would tear apart the gas clouds before they could collapse. How these stars formed remains a mystery, though there are theories involving gas clouds that were dense and massive enough to resist disruption, or stars that formed farther out and somehow migrated inward. The supermassive black hole at our galaxy's centre is more than just a fascinating object in its own right. It plays a crucial role in the galaxy's dynamics and evolution. Its gravity helps shape the orbits of stars in the central bulge. The energy it occasionally releases can heat gas and prevent it from cooling and forming stars, providing a form of feedback that regulates star formation in the galaxy's centre. And its very existence tells us something about how galaxies form and evolve. Nearly every large galaxy we've observed has a supermassive black hole at its centre. The mass of these black holes correlates remarkably well with the properties of the galaxy's bulge, suggesting that the black hole and galaxy grew together through a process astronomers are still working to understand fully. Did the black hole form first and help the galaxy form around it? Or did the galaxy form first and gradually feed the black hole? Or did they grow together in lockstep? These questions remain areas of active research. Sagittarius A is our closest supermassive black hole, making it one of our best laboratories for studying these enigmatic objects. Every observation, every measurement, every image adds to our understanding of how black holes work, how they influence their surroundings, and what happens to matter and energy in the most extreme gravitational environments in the universe. It's a dark heart, certainly, but one that illuminates much about the cosmos. The Milky Way is not a static museum piece. It's a living, evolving system where new stars are being born even as old stars are dying. To understand the galaxy's history and future, we need to understand its stellar populations, the different types of stars that inhabit different regions, and the ongoing process of star formation that continues to this day. Astronomers divide stars into populations based on their age and chemical composition. Population stars are young and metal-rich. In astronomy, metal means any element heavier than helium, which sounds strange until you realize that to an astronomer, even carbon, nitrogen, and oxygen are metals. Population I stars contain a relatively high percentage of these heavy elements because they formed from gas that had been enriched by previous generations of stars. Our Sun is a population 1 star containing about 2% heavy elements by mass. Population 2 stars are old and metal poor. They formed earlier in the galaxy's history when the interstellar medium hadn't been enriched as much by supernovae. These stars contain far less than 1% heavy elements. They're found primarily in the galactic halo, in globular clusters, and in the thick disk. Their low metallicity is like a timestamp, telling us they formed billions of years ago before many generations of massive stars had died and scattered heavy elements into space. There's also a theoretical population 3, which we mentioned earlier. These would be the very first stars, formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium. They would have been massive, short-lived, and fundamentally different from any stars we see today. None have been observed directly because they all died billions of years ago, but astronomers continue to search for them in the most distant, earliest galaxies visible with our most powerful telescopes. The different stellar populations tell a story of chemical evolution. When the universe began, there were no heavy elements. The Big Bang produced hydrogen, helium, and a tiny bit of lithium, but nothing else. Carbon, the basis of life, didn't exist. Oxygen, which makes up much of Earth's mass and the air we breathe, didn't exist. Iron, nickel, silicon, all the elements that make up planets and life, had to be created inside stars. This happens through nuclear fusion and supernova explosions. Inside stars, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The process continues, building heavier and heavier elements up to iron. Elements heavier than iron require energy input rather than releasing energy, so they are only created in the extreme conditions of supernova explosions or neutron star mergers. When a massive star explodes as a supernova, it scatters these newly forged elements into space. The blast wave compresses nearby gas clouds, sometimes triggering new star formation. The next generation of stars forms from gas that's been enriched with heavy elements. Those stars fuse more elements, die in their own supernovae, and enrich the gas further. Generation after generation, the metallicity of the interstellar medium gradually increases. This is why astronomers can use metallicity as a rough clock. Low metallicity means an old star formed long ago. High metallicity means a younger star formed more recently. It's not perfect because gas can be mixed and metal-poor gas can survive in some regions while metal-rich gas accumulates in others. But it's a useful general principle. Star formation in the Milky Way today is concentrated in the thin disk, particularly in the spiral arms. When we look at images of the galaxy in ultraviolet or infrared light, which reveal hot young stars and warm dust respectively, the spiral arms light up brilliantly. These are the active star-forming regions, the stellar nurseries where new suns are being born. One of the most famous star-forming regions visible from Earth is the Orion Nebula, located about 1,300 light-years away in the Orion Arm. On a dark night, it's visible to the naked eye as a fuzzy patch in Orion's sword. Through a telescope, it reveals itself as a glowing cloud of gas and dust, illuminated by hot young stars at its centre. These stars, part of a cluster called the Trapezium, are less than 1 million years old, newborns by astronomical standards. The Orion Nebula is a stellar nursery in action. Within its clouds, dense regions are collapsing under their own gravity to form new stars. The process begins when something triggers the collapse of a gas cloud. It might be a nearby supernova blast wave, the compression from a spiral arm density wave, or simply the random motion of gas that happens to accumulate in one spot. As the cloud collapses, it fragments into smaller clumps. Each clump continues to collapse, heating up as gravitational potential energy converts to thermal energy. Eventually, the core becomes hot enough for nuclear fusion to ignite, and a new star is born. The whole process takes millions of years for a sun-like star, but can happen faster for more massive stars. Many stars don't form in isolation. They form in clusters, groups of hundreds or thousands of stars born from the same giant molecular cloud. The Pleiades, that tight cluster of bright stars visible in the constellation Taurus, is a young open cluster about 100 million years old. Its stars form together and are slowly drifting apart as they orbit the galaxy. In another few 100 million years, they'll be scattered throughout the disk, their common origin only revealed by careful analysis of their velocities and positions. The rate of star formation in the Milky Way today is surprisingly modest. Our galaxy produces roughly 1 to 3 new solar masses of stars per year. That might sound like a lot, but spread across the entire galaxy, it means that at any given moment only a tiny fraction of the gas is actively forming stars. Most of the gas just sits there, too warm or too diffuse to collapse. This is actually a bit of a mystery. The galaxy contains billions of solar masses of gas, enough to form billions of new stars. So why isn't star formation happening more rapidly? The answer seems to involve feedback processes that regulate star formation. When massive stars form, they don't just shine passively. They emit intense ultraviolet radiation that heats and ionizes the surrounding gas. They drive powerful stellar winds that push gas away. And when they explode as supernovae, they inject tremendous energy into the surrounding region. All of this feedback disrupts nearby gas clouds and prevents them from collapsing to form new stars. It's a self-regulating process. Star formation creates conditions that suppress further star formation, at least locally and temporarily. Eventually the energy dissipates, the gas cools and settles, and new star formation can begin. It's a cycle that's been going on for billions of years and will continue for billions more. Different regions of the galaxy have different star formation rates. The inner galaxy, within about 10,000 light-years of the center, has relatively little star formation today despite having plenty of gas. The conditions there may be too turbulent, with strong gravitational tides from the bar and frequent shock waves that heat the gas. The peak of star formation seems to occur in a ring at a radius of about 13,000 to 20,000 light-years, which includes our location in the Orion Arm. The outer galaxy has less gas and fewer young stars. Star formation hasn't ceased completely in the outer disk, but it's much less vigorous than in the middle regions. This creates a radial gradient in stellar populations, with the inner disk containing more older stars and the outer disk being sparser and less active. The Milky Way's current star formation rate is much lower than it was in the past. We know this from studying stellar ages. There was a peak of star formation around 11 billion years ago during the Gaia-Enceladus merger, as we discussed earlier. Since then, the rate has been gradually declining. The galaxy is slowly running out of gas, or rather it's using up gas faster than new gas is falling in from the intergalactic medium. This is part of a natural aging process for galaxies. Young galaxies tend to have vigorous star formation, lots of gas and blue colors from all their massive young stars. As galaxies age, they use up their gas, star formation declines, and they gradually turn redder as the massive blue stars die, and the longer-lived red and yellow stars come to dominate. The Milky Way is middle-aged by this measure, past its peak of star formation but still actively forming stars. Individual stars have their own life cycles that play out over vastly different timescales depending on their mass. The most massive stars, those with tens of times the Sun's mass, burn through their fuel in just a few million years. They live fast and die young, exploding as spectacular supernovae that can briefly outshine entire galaxies. These stars are rare, but they have an outsized impact on the galaxy because of their intense radiation, strong winds, and explosive deaths. Medium-sized stars like our Sun live much longer, around 10 billion years. They spend most of that time steadily fusing hydrogen into helium, maintaining a stable balance between gravity pulling inward and pressure pushing outward. When they run out of hydrogen fuel in their cores, they swell into red giants, fuse helium briefly, then shed their outer layers and fade away as white dwarfs. This is the fate that awaits our Sun in about 5 billion years. Small stars, those with less than half the Sun's mass, are the most numerous and longest lived. A red dwarf with 10% of the Sun's mass will live for trillions of years, far longer than the current age of the universe. None of these small stars have ever died naturally yet because the universe isn't old enough. They'll be the last stars shining when all the massive stars have long since exploded, and even sun-like stars have faded to black dwarf cinders. This mix of stellar populations, from ancient halo giants to newborn protostars still wrapped in their birth clouds, gives the Milky Way its character and its ongoing vitality. Every clear night, if we look up, we're seeing stars of different ages, different compositions, different fates. Some are older than the solar system, witnesses to the galaxy's youth. Some are younger than human civilization, newborns in cosmic terms. And somewhere in the galaxy right now, hidden inside a dark cloud of gas and dust, a new star is igniting, beginning its own journey through the cosmos. There's something deeply unsettling about the fact that most of the Milky Way is invisible. We can map the stars, trace the spiral arms, measure the gas clouds, But all of that luminous matter accounts for only about 15% of the galaxy's mass. The other 85% is something we can't see, can't touch, and still don't fully understand. We call it dark matter, and it's absolutely essential to everything we observe. The story of dark matter begins with a puzzle noticed by astronomers in the 1970s. They were measuring how fast stars orbit at different distances from the galactic center. Based on the visible mass of the galaxy, they could calculate what the rotation curve should look like. Stars closer to the center should orbit faster, and stars farther out should orbit more slowly, following the same pattern that planets in our solar system follow around the Sun. But that's not what they observed. Instead, they found that stars in the outer parts of the galaxy were moving much faster than expected. In fact, stars at almost any distance from the center were orbiting at roughly the same speed, about 200 to 250 kilometers per second. This flat rotation curve was completely unexpected and couldn't be explained by the visible matter alone. There were only a few possible explanations. Either our understanding of gravity was wrong, or there was a lot more mass in the galaxy than we could see. Most astronomers favored the second option, not because it was comfortable, but because gravity had been tested extensively in other contexts and worked perfectly. The idea of invisible mass was strange, but modifying gravity would require throwing out a theory that worked everywhere else. The dark matter needed to explain the rotation curve has a specific distribution. It can't be concentrated in the disk or bulge because we'd see its gravitational effects on stars there. Instead, it must be in a roughly spherical halo extending far beyond the visible disk. This dark matter halo is what provides the extra gravity needed to keep the outer stars moving as fast as they do. But what is dark matter made of? This is one of the biggest unsolved problems in physics. We know what it's not. It's not regular matter that just happens to be dark like planets or black holes or dust. There's simply not enough of that to account for the missing mass, and besides, such objects would have other observable effects that we don't see. Instead, dark matter seems to be some exotic type of particle that doesn't interact with light or normal matter except through gravity. Various candidates have been proposed. WIMPs, or weakly interacting massive particles, were the favourite for many years. Axions, hypothetical particles much lighter than electrons, are another possibility. Sterile neutrinos, massive cousins of the ghostly neutrinos we know exist, have also been suggested. Despite decades of searching, we haven't directly detected dark matter particles yet. Experiments deep underground, shielded from cosmic rays, have been waiting patiently for a dark matter particle to collide with their detectors. So far, nothing definitive. The Large Hadron Collider has been smashing particles together at high energies, hoping to create dark matter in the lab. No luck yet. Astronomers keep searching for any sign that dark matter particles might occasionally decay or interact in some detectable way. The search continues. The lack of direct detection is frustrating, but it doesn't mean dark matter doesn't exist. The gravitational evidence is overwhelming and comes from many independent sources. Beyond rotation curves, we see dark matter's effects in how galaxy clusters hold together, in how light is bent when it passes near massive objects, and in the pattern of fluctuations in the cosmic microwave background radiation left over from the Big Bang. In fact, dark matter was essential for galaxy formation itself. In the early universe, before any stars had formed, ordinary matter was too hot and too strongly affected by radiation pressure to collapse into galaxies. But dark matter, which doesn't interact with radiation, could start clumping together immediately. These dark matter halos formed the gravitational wells that ordinary matter later fell into, allowing galaxies to form. Without dark matter, the universe might never have developed the large-scale structure we see today. The Milky Way's dark matter halo extends much farther than the visible stars. While the disk of stars ends at about 60,000 light-years from the center, the dark matter halo probably continues to at least 300,000 light-years, possibly as far as 600,000 light-years. That's 6 times the diameter of the visible galaxy, an enormous region of space dominated by this invisible substance. The shape of the dark matter halo is still being studied. Computer simulations suggest it might not be perfectly spherical. It could be somewhat flattened or even triaxial, shaped more like an American football or a watermelon than a perfect sphere. The distribution might also have substructure, clumps and streams of dark matter left over from smaller dark matter halos that merged into the Milky Way billions of years ago. These dark matter streams are particularly interesting. When a small galaxy falls into the Milky Way, its stars can be scattered and its dark matter halo disrupted, creating long streams that orbit through the galaxy. Astronomers are actively searching for these streams by looking for groups of stars moving together with similar velocities. Where there are stellar streams, there should be dark matter streams following the same paths. The density of dark matter in the solar neighborhood is about 1 proton mass per 4 cubic centimeters. That sounds incredibly diffuse, and it is by terrestrial standards. But over the huge volumes of space we're talking about, it adds up to enormous total mass. There are probably millions of dark matter particles passing through your body every second, but they interact so weakly that they pass right through without leaving any trace. This invisibility is both a blessing and a curse for astronomers. It makes dark matter incredibly difficult to study directly, but it also means dark matter doesn't complicate observations by glowing or obscuring things. We can see right through the dark matter halo to distant galaxies beyond. It's only through careful analysis of gravitational effects that we can map where dark matter is and how it's distributed. The relationship between dark matter and the visible galaxy is complex and not fully understood. Dark matter provides the gravitational scaffolding, but the ordinary matter, the stars and gas we can see, is what makes a galaxy interesting and dynamic. The two components influence each other. The dark matter's gravity holds everything together and shapes the large-scale structure. The ordinary matter's behavior, star formation, supernova explosions, black hole feedback, can actually affect the distribution of dark matter on smaller scales. Some theories suggest that the disk of the Milky Way might even contain a thin component of dark matter, concentrated in the galactic plane. This is controversial and not yet confirmed, but if true, it would make dark matter detection experiments more sensitive because the local density would be higher than in a purely spherical halo. The dark matter halo also plays a role in the Milky Way's interactions with other galaxies. When satellite galaxies orbit the Milky Way, they're orbiting through both the visible matter and the dark matter halo. The dark matter provides most of the gravitational pull that keeps them bound. Over time, tidal forces from the Milky Way's gravity can strip away both the stars and dark matter from these satellites, gradually dissolving them into streams. One of the most profound implications of dark matter is philosophical. We live in a universe where most of the matter is completely invisible to us. Everything we can see, every star, every planet, every galaxy, is just the tip of the iceberg, a small fraction of what's really there. It's humbling and also exciting. There are fundamental mysteries still to be solved, particles still to be discovered, and perhaps entirely new physics waiting to be uncovered. As detection experiments become more sensitive and observational techniques improve, there's hope that we'll finally identify dark matter's true nature. When that happens, it will be one of the greatest discoveries in the history of science, revealing the composition of most of the universe. Until then, dark matter remains a ghost, invisible but ever present, holding the Milky Way together through its gravitational embrace. The Milky Way doesn't exist in isolation. It's surrounded by a retinue of smaller companion galaxies, gravitationally bound to us and orbiting through our dark matter halo. Some of these satellites are substantial enough to be visible to the naked eye. Others are so faint that they were only discovered in the last few decades with sensitive sky surveys. Together, they tell a story of hierarchy, of how large structures like the Milky Way grow by consuming smaller ones, and how that process continues to this day. The most famous of the Milky Way satellites are the large and small Magellanic Clouds, often abbreviated as the LMC and SMC. These two irregular dwarf galaxies are visible from the southern hemisphere as fuzzy patches of light, looking almost like detached pieces of the Milky Way itself. Ancient peoples in the southern hemisphere knew about them for thousands of years, but they were brought to European attention by Ferdinand Magellan's expedition in the early 1500s, hence their name. The Large Magellanic Cloud is about 160,000 light-years away from us, making it one of the closest galaxies to the Milky Way. It contains about 20 billion stars and is actively forming new stars in several prominent nebulae, including the famous Tarantula Nebula, one of the most vigorous star-forming regions in the entire local group. The LMC is substantial enough that it has its own small retinue of satellite galaxies. The small Magellanic Cloud is slightly farther away, about 200,000 light-years distant and smaller, containing only a few billion stars. Both Magellanic Clouds are irregular in shape rather than being neat spirals or ellipticals. They're distorted by their interaction with each other and with the Milky Way, stretched and warped by tidal forces. In fact, the Magellanic Clouds are connected by a bridge of gas called the Magellanic Bridge, and are leaving behind them a long stream of gas called the Magellanic Stream. This stream stretches across more than 100 degrees of the sky, wrapping partially around the Milky Way. It's evidence of how tidal forces strip material from satellite galaxies as they orbit, gradually feeding that material into the larger galaxy. The fate of the Magellanic Clouds is still being studied. For a long time, astronomers thought they were in a stable orbit around the Milky Way, making many loops over billions of years. But recent measurements of their velocities using the Hubble Space Telescope and Gaia satellite suggest they might be moving faster than previously thought. If that's the case, they might be on their first pass by the Milky Way rather than being long-term satellites. They might eventually escape back into intergalactic space, or they might be captured and eventually torn apart and merged into the Milky Way over the next few billion years. Beyond the Magellanic Clouds, the Milky Way has dozens of smaller satellite galaxies. The exact count depends on how you define a galaxy versus a star cluster, but there are at least 50 known satellites and probably more waiting to be discovered. Most are dwarf spheroidal galaxies, small collections of stars with little or no gas and no ongoing star formation. These dwarf satellites are tiny compared to the Milky Way, containing anywhere from thousands to a few million stars. Some are so faint that they're incredibly difficult to detect. Segway 1, one of the faintest known satellites, contains only about 1,000 stars and has a total luminosity of just a few hundred suns. It's barely brighter than many globular clusters, and it was only discovered in 2006 during the Sloan Digital Sky Survey. One particularly interesting satellite is the Sagittarius Dwarf Elliptical Galaxy, not to be confused with Sagittarius A at the galactic center. This dwarf galaxy is in the process of being torn apart by the Milky Way's gravity. It's only about 70,000 light-years from the galactic center, well within the Milky Way's disk, and it's being stretched into long streams of stars that wrap around the galaxy. The Sagittarius dwarf was only discovered in 1994 despite being relatively close and large, about 10,000 times the luminosity of the Sun. The reason it remained hidden for so long is that it's located on the far side of the galactic center from us, behind the dense star fields and obscuring dust of the galactic bulge. Only careful analysis of star velocities revealed that there was a coherent structure there, a separate population of stars moving together through the Milky Way. Studies of the Sagittarius dwarf and its tidal streams have revealed something surprising. Several of the Milky Way's globular clusters, including M54 and possibly others, actually originated in the Sagittarius dwarf. They were once part of that satellite galaxy, but as the dwarf was torn apart, these clusters were stripped away. Now they orbit the Milky Way independently, though their orbits still follow the path of the Sagittarius stream. This is a common pattern. When a satellite galaxy is disrupted, its stars and any globular clusters it contains are scattered along its orbital path, creating a stream. Over time, the stream spreads out and becomes more diffuse, eventually mixing with the stellar halo. But for hundreds of millions, or even a few billion years, the stream remains coherent enough to be detected and studied. Astronomers have identified numerous stellar streams in the Milky Way's halo. There's the Helmy Stream, probably the remnant of a dwarf galaxy that merged with the Milky Way billions of years ago. The Orphan Stream is a mysterious feature whose parent galaxy hasn't been identified. The GD1 stream is a thin tidal stream that might have originated from a globular cluster rather than a galaxy. Each of these streams is a fossil, a relic of a past merger or disruption event. By studying these streams, astronomers can learn about the Milky Way's merger history and about the distribution of dark matter in the galaxy. As a stream orbits through the halo, it's affected by the gravitational pull of the dark matter. The stream's shape and density can be used to map the dark matter distribution. In fact, stellar streams are one of the best tools we have for studying dark matter on galactic scales. The existence of so many satellite galaxies around the Milky Way confirms theoretical predictions about galaxy formation. In the standard cosmological model, galaxies form hierarchically, with small structures forming first and then merging to build larger ones. The Milky Way should be surrounded by hundreds or even thousands of small dark matter halos, the remnants of structures that never grew into full-size galaxies. Most of these halos would be dark, containing no stars at all, but some should have formed a few stars and become visible as dwarf satellite galaxies. For a while there was actually a problem. Simulations predicted many more satellites than were observed, a discrepancy called the missing satellites problem. But as surveys have become more sensitive, more and more ultra-faint dwarf galaxies have been discovered. The observed number is catching up to the predictions, though there are still some puzzles about the properties of the smallest satellites. These tiny satellites are important for another reason. They're among the most dark matter-dominated objects known. A typical dwarf spheroidal might have a mass-to-light ratio of 100 or more, meaning it contains 100 times more mass in dark matter than in stars. Some ultra-faint dwarfs might be even more extreme. This makes them excellent laboratories for studying dark matter. If dark matter particles occasionally decay or annihilate, producing a flash of gamma rays, these dark matter-rich satellites might be the best places to look. The satellite galaxies also preserve information about the early universe. Because they're small, they have weak gravity and are easily disrupted by energetic processes like supernovae. This means they had trouble retaining gas after their first generation of star formation. Many dwarf spheroidals formed all their stars billions of years ago and haven't formed new stars since. This makes them fossils from the early universe, collections of ancient stars with low metallicity that can tell us what conditions were like in the first few billion years after the Big Bang. Some satellites show signs of having had their star formation quenched by the Milky Way itself. As a dwarf galaxy orbits through the Milky Way's halo, it encounters the Milky Way's own gas. This ram pressure can strip away the dwarf's gas, preventing further star formation. The satellite continues to exist as a collection of old stars, but it's been sterilized, unable to form new generations. The relationship between the Milky Way and its satellites is not entirely one-sided. While the Milky Way is clearly the dominant partner, gravitationally disrupting and eventually consuming the satellites also affect the Milky Way. Each merger adds mass, stars, and dark matter to the Milky Way. The perturbations from orbiting satellites can stir up the disk, creating ripples and waves in the stellar distribution. There's even evidence that the large Magellanic Cloud, despite being a satellite, has had a significant impact on the Milky Way. Recent simulations suggest that the LMC's gravity might have pulled on the Milky Way's disk, contributing to some of the warps and asymmetries we observe. The LMC is massive enough, with about 10% of the Milky Way's mass in stars and possibly more in dark matter, that its gravitational influence is not negligible. Looking to the future, the Milky Way will continue to accrete its satellites. The process that built the galaxy over the past 13 billion years hasn't stopped. Some satellites will be torn apart over the next few billion years, their stars scattered into the halo. Others might survive longer, depending on their orbits and how much dark matter they contain to hold them together. And new satellites might even fall in from the intergalactic medium, small dwarf galaxies that are currently unbound but will eventually be captured by the Milky Way's gravity. The study of satellite galaxies and stellar streams has been revolutionized by recent surveys. The Sloan Digital Sky Survey, which mapped millions of stars, discovered many new ultra-faint satellites. The Gaia mission, which is measuring precise positions and velocities for over 1 billion stars, has revealed new streams and helped trace the orbits of known satellites. Future surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will undoubtedly discover even more of these faint structures. Each satellite, each stream, each fossil of an ancient merger is a piece of the puzzle of the Milky Way's history. Together, They tell a story of growth through accumulation, of a large galaxy that built itself by consuming countless smaller galaxies over billions of years. It's a somewhat violent story, but it's also the story of how structure emerged from the primordial smoothness of the early universe. And it's a story that's still being written, with each new observation adding another chapter to our understanding of our galactic home. The Milky Way might be the center of our astronomical perspective, but on a cosmic scale it's just one member of a larger community. The LMC is massive enough, with about 10% of the Milky Way's mass in stars and possibly more in dark matter, that its gravitational influence is not negligible. Looking to the future, the Milky Way will continue to accrete its satellites. The process that built the galaxy over the past 13 billion years hasn't stopped. Some satellites will be torn apart over the next few billion years, their stars scattered into the halo. Others might survive longer, depending on their orbits and how much dark matter they contain to hold them together. And new satellites might even fall in from the intergalactic medium, small dwarf galaxies that are currently unbound but will eventually be captured by the Milky Way's gravity. The study of satellite galaxies and stellar streams has been revolutionized by recent surveys. The Sloan Digital Sky Survey, which mapped millions of stars, discovered many new ultra-faint satellites. The Gaia mission, which is measuring precise positions and velocities for over 1 billion stars, has revealed new streams and helped trace the orbits of known satellites. Future surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will undoubtedly discover even more of these faint structures. Each satellite, each stream, each fossil of an ancient merger is a piece of the puzzle of the Milky Way's history. Together, they tell a story of growth through accumulation, of a large galaxy that built itself by consuming countless smaller galaxies over billions of years. It's a somewhat violent story, but it's also the story of how structure emerged from the primordial smoothness of the early universe. And it's a story that's still being written, with each new observation adding another chapter to our understanding of our galactic home. The Milky Way might be the center of our astronomical perspective, but on a cosmic scale it's just one member of a larger community. Our galaxy and its satellites are part of a gravitationally bound collection of galaxies called the Local Group, a gathering of more than 80 galaxies spread across about 10 million light-years of space. Understanding the Local Group helps us see the Milky Way in context and appreciate our place in the larger structure of the universe. The Local Group is dominated by two large spiral galaxies, our Milky Way and the Andromeda Galaxy, also known as Messier 31 or M31. These two giants are by far the most massive members of the group, each with hundreds of billions of stars. Andromeda is actually somewhat larger and more massive than the Milky Way, containing perhaps 1 trillion stars compared to our few hundred billion. It's also closer to us than any other large galaxy, sitting about 2.5 million light-years away. From Earth, Andromeda is visible to the naked eye as a faint smudge in the constellation Andromeda. It's one of the most distant objects visible without a telescope, and when you look at it, you're seeing light that left those stars 2.5 million years ago, when our human ancestors were just beginning to walk upright on the plains of Africa. Through a telescope or in long exposure photographs, Andromeda reveals itself as a magnificent spiral galaxy, tilted so we see it at an angle rather than face on. Like the Milky Way, Andromeda is a barred spiral galaxy with prominent spiral arms, a central bulge and a disk of stars. It has its own collection of satellite galaxies, including M32 and M110, two dwarf elliptical galaxies that orbit closely and are visible in modest telescopes. Andromeda also has a massive dark matter halo, and it has experienced its own history of mergers and interactions. The third notable member of the Local Group is the Triangulum Galaxy, M33, a smaller spiral galaxy about 3 million light-years away. Triangulum contains about 40 billion stars, making it substantial but much smaller than either the Milky Way or Andromeda. It's also notable for being relatively face-on from our perspective, giving us a beautiful view of its spiral structure. Under excellent dark sky conditions, Triangulum is just barely visible to the naked eye, making it the most distant object regularly visible without optical aid. The relationship between these three spirals is complex. For a long time, astronomers thought Triangulum might be a satellite of Andromeda, orbiting the larger galaxy. But recent measurements suggest it might not be bound to Andromeda after all, or if it is, the relationship is much more tenuous than previously thought. It's possible that all three galaxies are interacting as part of a loose triplet rather than having a clear hierarchy. Beyond these three major spirals, the local group contains dozens of dwarf galaxies. We've already discussed the Milky Way satellites, but Andromeda has its own extensive collection. In fact, Andromeda seems to have even more satellites than the Milky Way, consistent with it being the more massive galaxy. Some of these satellites are relatively substantial, while others are ultra-faint dwarfs that push the definition of what counts as a galaxy versus a large star cluster. There are also a handful of irregular dwarf galaxies in the local group that don't clearly belong to either the Milky Way or Andromeda. The large and small Magellanic Clouds are the largest examples, though as we discussed, they're gravitationally bound to the Milky Way. There are smaller examples like the Sagittarius dwarf irregular galaxy, not to be confused with the Sagittarius dwarf elliptical that's being torn apart, or IC10, a small irregular galaxy that's actually quite active in star formation despite its small size. The distribution of galaxies in the local group is not random. The galaxies are spread out through space, but they're concentrated around the two major members. There's a Milky Way subgroup consisting of us and our satellites, and an Andromeda subgroup consisting of Andromeda and its satellites. These two subgroups are separated by about 2.5 million light-years, and crucially they're moving toward each other. This brings us to one of the most dramatic facts about the local group. It's not stable. The Milky Way and Andromeda are on a collision course. We'll discuss this in much more detail in the next section, but it's worth mentioning here because it fundamentally affects the future of the local group. In a few billion years, the current structure of two dominant galaxies with their separate satellites will be replaced by a single massive elliptical galaxy formed from the merger. The local group as a whole is moving through space. Like everything in the universe, it's part of larger structures. The local group is on the outskirts of the Virgo supercluster, an enormous collection of galaxies centered on the Virgo cluster about 50 million light-years away. More recently, astronomers have realized that the Virgo supercluster is itself part of an even larger structure called the Laniakea supercluster, which spans 500 million light-years and contains about 100,000 galaxies. But these superclusters aren't tightly bound like the local group. The expansion of the universe means that distant galaxies are moving away from us faster than gravity can pull them together. The local group is one of the few structures at this scale that's actually gravitationally bound, meaning the galaxies within it will stay together even as the universe continues to expand. Everything outside the local group beyond about 10 million light-years is gradually receding from us and will eventually disappear beyond our cosmic horizon. Within the local group, there's also a curious void. The region between the Milky Way and Andromeda subgroups is relatively empty with few galaxies. This might be because any dwarf galaxies that formed there have already been captured by one of the two major galaxies, or it might simply be a statistical fluctuation in how galaxies formed. Either way, it creates an interesting bimodal distribution with two concentrations of galaxies separated by relatively empty space. The dynamics of the local group are still being studied. Astronomers use observations of galaxy positions and velocities to build models of how the group formed and how it's evolving. These models need to account for not just the visible matter in galaxies, but also the dark matter halos surrounding each galaxy, and the overall dark matter distribution in the local group. The motions of galaxies through this dark matter landscape are what determine their future trajectories. One interesting aspect of the local group is that it gives us a laboratory for studying galaxy evolution in a relatively low-density environment. In rich galaxy clusters, galaxies are packed more tightly together and interact more frequently. The intense environment of clusters can strip gas from galaxies, trigger bursts of star formation, or even rip galaxies apart through tidal forces. But the local group is more sedate. Galaxies interact certainly, but at a more leisurely pace. This might be important for understanding why the Milky Way and Andromeda remain actively star-forming spiral galaxies, rather than having merged long ago into a red and dead elliptical. We've had time to develop our structure, to form our disks and spiral arms, without being constantly battered by interactions with other large galaxies. Of course, that's about to change, but we've had billions of years of relative peace first. The future of the local group is tied to the fate of its two dominant members. As the Milky Way and Andromeda approach each other and eventually merge, the smaller galaxies will be caught up in the chaos. Some will be flung out into intergalactic space by gravitational slingshot effects. Others will fall into the merged galaxy and be consumed. The neat organization of satellites around two major galaxies will be replaced by a more chaotic distribution. Far in the future, tens of billions of years from now, the merged Milky Way Andromeda galaxy, and perhaps Triangulum if it's still around and gets pulled into the merger, will be essentially the only galaxy visible in the sky. Everything else in the local group will have either merged or been flung away, and everything beyond the local group will have been carried so far away by cosmic expansion that it will be beyond the reach of our telescopes. Future astronomers will live in a universe that appears much emptier than ours, with just one massive galaxy in an otherwise seemingly empty cosmos. But we're getting ahead of ourselves. For now, the local group remains a diverse collection of galaxies, from massive spirals to tiny ultra-faint dwarfs, all bound together by gravity and destined to continue interacting and merging as cosmic time marches forward. It's our immediate cosmic neighborhood, and studying it helps us understand not just our own galaxy, but galaxy evolution in general. The night sky feels eternal. The constellations our ancestors knew are essentially unchanged. The stars seem fixed in their positions, permanent and unchanging. But this apparent stability is an illusion created by the vastness of time and space. In reality, the Milky Way and everything in it is moving, and we're on a collision course with our nearest large neighbor. The Andromeda Galaxy, that faint smudge visible in autumn skies, is hurtling toward us at about 110 kilometers per second. That's approximately 250,000 miles per hour, fast enough to cross the distance from Earth to the Moon in just over an hour. At the same time, we're moving toward Andromeda, drawn together by our mutual gravitational attraction. The combined closing speed means that in about 4 to 5 billion years, the two galaxies will collide. Let's be clear about what a galaxy collision means. This isn't like two solid objects smashing into each other. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, actual collisions between individual stars are extraordinarily rare. You could live on a planet in either galaxy through the entire merger and never worry about another star getting dangerously close to your solar system. But while stellar collisions are rare, the gravitational interactions are profound. As the two galaxies approach each other, their mutual gravity begins to distort them. The Milky Way will raise tidal bulges on Andromeda, and Andromeda will do the same to us. These tidal forces will stretch and warp the neat spiral structure of both galaxies, pulling out long streamers of stars that extend into space. Computer simulations have given us a preview of what this merger might look like. About 4 billion years from now, Andromeda will first become visible as a distinct disk in our night sky rather than a faint fuzzy patch. As it gets closer over the next several 100 million years, it will grow larger and brighter, eventually dominating the night sky as a gigantic glowing band of stars stretching across the celestial sphere. The first close pass will be dramatic. The two galactic disks will interpenetrate, passing through each other like ghosts. But the gravitational effects will be anything but ghostly. Stars will be flung into new orbits. The neat spiral arms will be disrupted. Gas clouds will collide, and this collision of gas will be much more violent than the passage of stars. When two gas clouds slam into each other at high speed, they compress and heat up. This triggers an enormous burst of star formation. The Milky Way and Andromeda will light up with brilliant blue-white new stars, forming at a rate far higher than either galaxy experiences today. If there are any astronomers still around to observe it, and if they're in a position to do astronomy rather than dealing with the chaos, they'll witness one of the most spectacular displays of cosmic fireworks in the universe. The combined galaxy will briefly become what's called a starburst galaxy, forming stars at rates hundreds or thousands of times faster than normal. After the first pass, the two galaxies won't merge immediately. They'll swing past each other, pulled apart slightly by their own momentum but unable to escape each other's gravity. They'll separate, but not completely. Then gravity will pull them back together for a second collision, and possibly a third. Each passage will dissipate more energy and bring the two cores closer together. Over 1 billion years or so, the two galaxies will gradually merge into a single structure. The organized disk structure of both galaxies will be destroyed, scrambled by the gravitational stirring. The stars will end up in orbits that are more random, less organized than the neat circular paths in the original disks. The final product will likely be a giant elliptical galaxy, a roughly spherical or slightly elongated collection of stars with no disk and no spiral arms. Astronomers have already given this future merged galaxy a name, Milkomeda, or sometimes Milkdromeda. It will be the dominant galaxy in the local group, containing well over 1 trillion stars, massive and bright. But it will also be relatively inactive. The burst of star formation triggered by the merger will consume much of the available gas. What gas remains will be heated and dispersed. Milkomeda will be a red and dead galaxy, containing mostly old stars with little new star formation. What about our solar system? What happens to Earth during this cosmic catastrophe? The good news is that direct danger from stellar collisions is minimal. The odds that another star will pass close enough to Earth to disrupt our orbit around the Sun are extremely small, even during the most chaotic phases of the merger. Stars are simply too far apart for collisions to be common. However, the gravitational disruptions could still affect us. The solar system's orbit around the galactic center will definitely be altered. We might be flung out into the outer regions of the merged galaxy, far from the new center. We might even be ejected entirely, thrown into intergalactic space to wander alone. On the other hand, we might sink closer to the center of Milkomeda, ending up in a more crowded neighborhood than we're used to. But there's a more immediate problem for Earth, one that has nothing to do with the Andromeda merger. In about 5 billion years, right around the same time as the first close pass with Andromeda, the Sun will begin its evolution into a red giant. As it exhausts the hydrogen fuel in its core, it will swell dramatically, possibly expanding to engulf the inner planets, including Earth. Even if Earth's orbit somehow manages to avoid being swallowed, the increase in solar radiation will make our planet uninhabitable long before then. So the merger with Andromeda, while dramatic on a galactic scale, is unlikely to be the thing that ends life on Earth. The Sun's evolution will take care of that first. Of course, if humanity or our descendants are still around in a few billion years, presumably we'll have either found a way to move Earth to a safer orbit, or more likely we'll have spread to other star systems. The merger might actually provide opportunities, creating new star systems and planets to colonize as gas clouds collapse to form new stars. After the merger is complete, perhaps 5 to 7 billion years from now, Milkomeda will begin a slower, quieter phase of evolution. The violent star formation will have subsided. The stars formed during the starburst will be aging. The most massive ones will have already exploded as supernovae. The galaxy will be dominated by older, cooler stars, giving it a reddish color rather than the blue-white of active star-forming galaxies. The supermassive black holes at the centers of the Milky Way and Andromeda, Sagittarius A and Andromeda's black hole, will also merge. As the two galactic cores spiral together, the black holes will eventually meet. They'll circle each other in an ever-tightening orbit, emitting gravitational waves that carry away energy and angular momentum. Finally, they'll merge in a catastrophic event that will send ripples through space-time detectable across the universe. The merged black hole will be enormous, containing more than 40 million solar masses. It will sit at the center of Milkomeda, the gravitational anchor of the new galaxy. Over time, it might occasionally flare up as it accretes gas and stars that wander too close. But mostly it will be quiet, a dark heart at the center of a slowly aging galaxy. The merger with Andromeda won't be the end of Milkomeda's evolution. The local group contains other galaxies that might also be incorporated over time. Triangulum, if it hasn't already merged with Andromeda before the main event, might eventually be pulled in. The various dwarf satellites of both galaxies will either merge or be ejected. Over tens of billions of years, essentially everything in the local group that isn't thrown out will become part of Milkomeda. Meanwhile, the rest of the universe will be moving away from us. The expansion of the universe means that distant galaxies are receding, and that recession is accelerating due to dark energy. Galaxies beyond the local group are already too far away to ever merge with us, and they're getting farther away all the time. Eventually, everything outside what becomes Milkomeda will be so distant that its light will no longer reach us. The observable universe will shrink down to just our local merged galaxy. This is a somewhat lonely fate, but it's many billions of years in the future. For now, we can appreciate the drama of what's coming. The Milky Way and Andromeda, two majestic spiral galaxies, are engaged in a slow gravitational dance that will end in a merger. It's a process that's played out countless times across the universe as galaxies collide and merge, building ever larger structures. We're fortunate, in a way, to have a front-row seat to one of these cosmic events, even if it will take billions of years to play out. Looking up at the night sky, knowing that Andromeda is creeping closer at hundreds of thousands of miles per hour, adds a dynamic quality to what seems static. The universe is not frozen. Everything is moving, evolving, changing on timescales that dwarf human lifetimes but are mere blinks in cosmic time. The galaxy we call home is not eternal in its current form. It has a past, a present, and a future, and that future includes a dramatic transformation. We've followed the Milky Way from its birth 13.6 billion years ago, through its violent youth, its period of consolidation and structure formation, its current mature state, and the upcoming merger with Andromeda. But the story doesn't end there. What happens to Milkomeda after the merger? What's the ultimate fate of our galaxy over truly cosmic timescales? To answer these questions, we need to think about the life cycle of stars and the slow death of galaxies. Star formation is the heartbeat of a galaxy. As long as a galaxy has gas that can collapse to form new stars, it remains vibrant and dynamic. New massive stars light up the galaxy with their brilliant blue-white light. They drive stellar winds that stir up the interstellar medium. When they die in spectacular supernovae, they enrich the gas with heavy elements and trigger new rounds of star formation. It's a self-sustaining cycle that can continue for billions of years, but this cycle requires fuel in the form of cold gas, primarily hydrogen, and that fuel is finite. The Milky Way currently contains several billion solar masses of gas available for star formation. At our current star formation rate of about 2 solar masses per year, that gas will last for several billion more years. But gas is also being lost. Hot gas is blown out of the galaxy by supernova explosions and stellar winds, escaping into intergalactic space where it's too diffuse and hot to return and form stars. The merger with Andromeda will consume much of the remaining gas in a burst of star formation. After that burst subsides, Milkomeda will have very little cold gas left. New star formation will slow to a trickle and eventually cease altogether. The galaxy will enter a phase called quiescence, where it's no longer actively forming stars. This is the fate of many galaxies in the universe, particularly massive elliptical galaxies that formed through mergers. They're red and dead, dominated by old stars with no new generations being born. Once star formation stops, the character of the galaxy changes slowly but inexorably. The most massive stars that exist when star formation ceases will die within a few million years. These blue giants and supergiants are the brightest stars in the galaxy, so their deaths will cause a noticeable dimming. Over the next few 100 million years, progressively less massive stars will exhaust their fuel and die. After 1 billion years, all stars more massive than about 3 solar masses will be gone. The galaxy will gradually become redder as the population shifts toward lower mass, cooler stars. Sun-like stars will evolve into red giants, swell up, shed their outer layers, and fade as white dwarfs. The galaxy's light will come increasingly from red giants and red dwarfs, those small, cool stars that burn their fuel so slowly they can last for trillions of years. By about 100 billion years after star formation ceases, essentially all stars except red dwarfs will have exhausted their fuel. The galaxy will contain white dwarfs, neutron stars, black holes, and countless red dwarfs still burning slowly. The white dwarfs will be cooling gradually, fading from white-hot to red to black, as they radiate away their residual heat. On these timescales, even white dwarfs don't last forever. But red dwarfs will keep going, A red dwarf with 10% of the Sun's mass will burn for 10 trillion years, 1,000 times longer than the current age of the universe. These tiny stars will be the last lights in the galaxy, slowly consuming their hydrogen fuel. During this era, Milkomeda will be a dim reddish galaxy, barely visible from any outside perspective if there were anyone out there to look. Eventually even red dwarfs will run out of fuel. The last stars will die perhaps 10 trillion years from now, give or take. When that happens, the galaxy will contain only stellar remnants, white dwarfs that have cooled to black dwarfs, neutron stars and black holes. There will be no light except perhaps occasional flashes when two white dwarfs collide or a star makes a close pass by the central black hole and is torn apart in a final death spasm. The structure of the galaxy will also evolve over these timescales. Close encounters between stars, though rare, will gradually randomize orbits and cause some stars to be flung out of the galaxy entirely. Over timescales of 10 to the power of 19 years, about a billion years, most of the stellar remnants will either fall into the central black hole or be ejected into intergalactic space. The galaxy will slowly evaporate. During this process, the supermassive black hole at the center will grow. Every stellar remnant that falls in adds to its mass. Binary star systems that spiral together and merge will occasionally produce gravitational waves that we could detect if we were still around. The black hole itself will gradually migrate toward the center of mass of the galaxy through a process called dynamical friction, where its gravity interacts with surrounding stars and slows its motion through any medium. Eventually, perhaps after 10 to the power of 20 years, most of the stellar remnants will be gone. The galaxy, if you can still call it that, will consist of a supermassive black hole surrounded by a sparse halo of stellar remnants that escaped ejection. It will be dark, cold, and essentially dead. But even this isn't the end. Black holes themselves may not be eternal. Stephen Hawking showed theoretically that black holes can evaporate through a quantum mechanical process now called Hawking radiation. A black hole slowly loses mass by emitting particles, a process so slow that even stellar mass black holes take 10 to the power of 67 years to evaporate completely. Supermassive black holes take even longer, with evaporation timescales of 10 to the power of 100 years or more. On these mind-boggling timescales, even the supermassive black hole at the center of Milkomeda will eventually evaporate. When it does, it will disappear in a final burst of radiation, possibly producing a mini fireworks display that no one will witness. After that, all that will remain of our galaxy will be a sparse cloud of elementary particles, photons and neutrinos mostly, drifting apart as the universe continues to expand. This is the ultimate heat death of the galaxy and indeed of the entire universe. All structure will have dissolved. All energy will have been degraded to its lowest possible state. The universe will be cold, dark, and essentially empty except for a thin soup of particles at a temperature barely above absolute zero. From the furious energy of the Big Bang to the cold silence of heat death, that's the arc of cosmic evolution. It's a sobering fate, but it's so far in the future that it's almost abstract. The timescales involve dwarf not just human history, but the entire age of the universe so far many times over. The heat death of the galaxy won't occur for at least 10 trillion years, possibly much longer. That's longer than the current age of the universe by a factor of 1,000 or more. In the meantime, before these unimaginable futures arrive, the Milky Way and Milkomeda will have a long period of activity and interest. Even after the merger with Andromeda, there will still be star formation for a while. There will be planetary systems, perhaps including ones with life. The galaxy will continue to be a dynamic, interesting place for billions of years after we're gone. And humanity or whatever we become might still be around for some of that. If we manage not to destroy ourselves, if we spread to other star systems and learn to thrive across interstellar distances, our descendants might witness the merger with Andromeda firsthand. They might watch as Milkomeda forms and evolves. They might even develop the technology to survive the death of stars, building artificial habitats powered by sources other than stellar fusion. There are theories, speculative certainly, about how advanced civilizations might survive even the heat death of the universe. Perhaps they could harvest energy from black holes using Penrose processes, or build computers that operate on quantum fluctuations in the vacuum. Perhaps they could find ways to slow time subjectively, making the long death of the universe pass quickly from their perspective. These are far beyond anything we can currently achieve, but over billions of years, who knows what might be possible. For now, we can appreciate the Milky Way as it exists today. We live in a special time, cosmically speaking. The universe is old enough to have formed complex structures like galaxies and stars and planets and life. But it's still young enough to be full of energy and light. Stars still shine, galaxies still collide and merge. New structures are still forming. This epoch, the stelliferous era as it's sometimes called, is when the universe is at its most interesting. Our galaxy, our cosmic home, is a mature spiral in its prime. It has survived a violent youth and will continue in its current form for billions more years before the merger with Andromeda reshapes it into something new. We're privileged to live during this time, to be able to look up at the night sky and see the band of the Milky Way stretching overhead, a view that connects us to our ancestors and to every human who has ever wondered about the cosmos. The Milky Way story is, in a sense, our story too. We're made of elements forged in the hearts of stars that lived and died in this galaxy billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created by stars and scattered by supernovae. We are literally made of stardust, assembled from the remnants of dead suns into complex arrangements that can somehow think and wonder and look back at the stars that made us. And so we come to the end of our journey through the history and future of the Milky Way. We've travelled from the earliest moments, when dark matter began to clump in the aftermath of the Big Bang, through the formation of the first stars, the violent collision with Gaia-Enceladus, and the development of the spiral structure we see today. We've explored the galaxy's anatomy, from the supermassive black hole at its heart to the dark matter halo that extends far beyond the visible stars. We've met the galaxy's companions, the satellite galaxies that orbit us and will eventually be consumed. We've seen our place in the local group and understood that the Milky Way, as grand as it is just one of many galaxies in the universe. We've looked forward to the dramatic merger with Andromeda and the birth of Milkomeda, and we've contemplated the distant future, when star formation will cease and the galaxy will slowly fade into darkness over unimaginable spans of time. What strikes me, having traced this entire history, is how dynamic everything is. When we look at the night sky, it seems eternal and unchanging. The stars appear fixed in their patterns. The Milky Way's band looks permanent and stable. But underneath that apparent stability is constant motion, constant change, constant evolution. Stars are being born and dying. Gas is flowing through the galaxy. Satellite galaxies are being torn apart, and the whole structure is slowly spinning, taking our solar system on a 230 million year journey around the centre. The Milky Way is not a thing, not a static object. It's a process, a pattern of matter and energy that maintains itself for a while before evolving into something new. It's been many different things over its 13.6 billion year history, and it will be many more things before it finally fades away in the unimaginably distant future. What does it mean to be part of this? We humans are brief flickers in the galaxy's lifetime. Our entire species has existed for only a few 100,000 years, less than 1% of 1% of the galaxy's age. An individual human life is measured in decades, lasting for perhaps a third of one orbit around the galaxy if you're fortunate. We're ephemeral, temporary, tiny, and yet we're also part of it. We're not separate from the galaxy, looking at it from outside. We're embedded in it, made of it, shaped by it. Every atom in your body was forged in a star that lived and died in this galaxy. You're literally a part of the Milky Way, a small portion of the galaxy that has become self-aware and can contemplate its own existence. When you look up at the night sky and see the Milky Way's band stretching across the darkness, you're not seeing something separate from you. You're seeing your home, your origin, your cosmic context. You're seeing the galaxy from inside, looking out at the other parts of yourself, in a sense. It's a profound connection that goes beyond metaphor. The Milky Way has given us more than just the raw materials of our bodies. It's given us a stable environment where complex chemistry could occur. Our solar system's location in the galactic suburbs, away from the crowded centre and the sparse outer edges, may have been crucial for life to develop. The relative calm of our neighbourhood, without too many nearby supernovae or close stellar encounters, gave evolution the time it needed to produce complex life. The heavy elements that make up Earth and everything on it, forged in generations of stars over billions of years, provided the palette from which life could be painted. The specific chemical enrichment history of the gas cloud that collapsed to form our solar system determined what materials were available to build planets and ultimately to build us.